Okay, so welcome back. So now you may have noticed, maybe you haven't, that all of the examples, the two examples that we did, resulted in the limit being equal to the number that you get when you evaluate the function at the limit. Okay, so what am I saying? Well, in the last one, we got 1/4. And so remember, the limit was this, right? What do we get? We have 2x squared minus 3x plus 1 over x cubed plus 4. Okay, what do we get? The limit was 1/4. Well, oops, this was 2. Okay, well, what happens if we evaluate this at 2? So we get 2 2 times 2 squared minus 3 times 2 plus 1, oops, 2 to the third plus 4. Isn't that what we ended up with? It sure is. This is exactly what we end up with at the very end, which gave us our 1/4. That brings us to theorem number 3, which has to do with polynomials. So remember about polynomials. How do polynomials behave? What's the characteristics of polynomials? They're continuous everywhere. Okay? They're defined everywhere in the number line. They're a smooth, continuous curve. Okay? So that means that the limit is going to exist everywhere. At any point that you're running towards or going towards, it will exist because we're dealing with a function that is a smooth, continuous curve. Okay, that's going to be important later. Okay, so that means that this theorem says that, hey, when we're dealing with polynomials, we can get the limit by just evaluating the functions at the limit. So in other words, let P of x and Q of x be polynomial functions. Let a be a real number. Then the limit as x approaches a of any polynomial will just be equal to P of a. So the polynomial function evaluated at the limit. Okay? And then the limit of the quotient of two polynomial functions is equal to the quotient of the two polynomial functions evaluated at the limit, provided again that Q of a is not equal to 0 for obvious reasons. Can't have 0 in the denominator. Okay? So this is theorem 3. Now we can apply this result to examples. Have a good day.